Hello, everyone. Welcome to the session. My name is Matthew Deng. I am a software engineering manager here at Anyscale. And in today's talk, I'll be going over the ray train library as a solution for overcoming challenges for efficient training at scale. So the agenda for this talk, I'll start by giving a little bit of background in some of the model training trends in recent years, and then transition into talking about the challenges that we're seeing in distributed training today. With this, we'll transition to an introduction of ray train and go over how it solves the challenges in distributed training, namely through ray train's integrations, observability, fault tolerance, and data ingestion capabilities. To wrap it up, we'll do a quick case study and review how we did pre-training with stable diffusion with ray train. Let's get started. So a little bit of background of model training trends. It should be obvious by now that in recent years, AI has grown significantly. We've seen larger models with a great boom in generative AI, especially in the past 2 years. Similarly, we've seen a massive growth in data needed for training such large models, and not just in the quantity of data, but also in different types of data modalities, such as text, images, audio, and video. And yes, there's been a similar increase in the amount of accelerators that are created to support this type of large-scale model training with large data, but one thing is inevitable. Even with these advancements in hardware, distributed training is necessary in order to handle the scale at which we need to compute model training. So, if we need distributed training, what are the common challenges that you might run into when scaling from a single instance to multiple instances? Some of the top challenges include setting up distributed environments for your particular ML framework, but also in connecting with your specific ML workflow. You might also run into trouble debugging distributed systems now, as well as figuring out how do you properly handle hardware failures. In addition to this, there's also this new challenge in which you need to manage large data complexity at such scale. So how do we tackle these challenges? For the rest of this talk, I'm going to describe ray train, a solution that we've built in Ray to handle large-scale training. So the first question that you're going to ask is, what is ray train? Ray train is a library that makes distributed training easy. It works with all of your favorite ML frameworks and enables you to do distributed training with your framework of choice. In addition to that, it's built on top of Ray, which allows you to know that you'll be able to scale your distributed training across whichever compute you may be using. With this context, let's dive into how it solves the challenges we mentioned earlier. First, let's talk about the challenge of setting up your distributed environment. To do this, I'm going to do a quick example, a quick start of ray train. So let's say you have some code that you need to write. How do you do this with ray train? The first step is that you'll want to define your training function in which you have your model training code. In this example, we commented out, but you might have your PyTorch training code, your TensorFlow training code, or your XGBoost training code. Whatever that may be, it should be familiar to you as someone who's already trained their model before in a single instance. The second step from there is that you'll want to start thinking about how do you configure scale. From RayTrain, we provide a simple interface called the scaling config, which allows you to define the scale at which you want to run your distributed training in just one line of Python. In this example, we have a scaling config that scales across 4 GPUs, and it really is as simple as that. To show you a few more examples of how easy it is, consider that you might want to scale across different types of accelerators. In the first example we have on the screen, we're simply scaling across a few CPU instances in which you could define how many CPUs you want each instance to use. The second example shows if beyond just using GPUs, you want to scale across a particular GPU type. In this case, you just want to use A100s. And the third example shows how you would configure your scaling config if you want to use a different type of accelerator. In this case, this is scaling across TPUs. So we talked about the training function and the scaling configuration. And the next step is to just package this up with the RayTrain library. And you can do so by using a RayTrain trainer interface. In this case, we have a PyTorch torch trainer, and this is the abstraction that will help set up your distributed torch environment for you. To tie it all together, you simply can launch distributed training by calling trainer.fit. Let's dive into this and see what's actually happening under the hood. The first thing that's going to happen when you call trainer.fit is RayTrain will take a look at your scaling config and start scaling the cluster according to the scale that you specified. Secondly, it'll launch worker processes across the cluster, again, based on your scaling configuration. The next thing that will happen is that RayTrain will set up the distributed environment for your particular framework of choice. In this case, I have a torch trainer, so it's setting up a PyTorch distributed environment across the worker processes. Next, it'll take your user-defined training function and start executing it across all of the worker processes. While running the training function, this is where the distributed training actually happens. In this case, if you have PyTorch distributed and you're running PyTorch code, you could use any of your favorite strategies to do the distributed training, whether it's PyTorch DDP, PyTorch FSDP, or DeepSpeed 0, being a few popular examples of what users are doing today. And yes, it's really that easy. So we talked really quickly through a quick start to show you what the simple interface of RayTrain looks like and how it helps with setting up a distributed environment for training. The next question that you might have is, well, that makes sense for a quick start, but what about my particular workflow? I have a very specific way of doing things. Is it going to work for me? And to answer that question, I'll quickly just show a slide that shows a few examples of some of the integrations that we've built with RayTrain. The reason why we've built all these integrations is because we know that the ML ecosystem is very fragmented. And you might have a different training framework, your own choice of experiment tracking tool, or a specific compute system or storage layer that you need to support. But fortunately, RayTrain was built with all of these in mind to make sure that RayTrain is composable with your ML workflow. The third challenge that we'll dive into now is a challenge that comes when scaling up to multiple instances, which is how do I debug a distributed system in the first place? Luckily, RayTrain comes with a built-in Ray dashboard. The Ray dashboard is a dashboard that's meant for debugging all your favorite Ray applications. It comes with a variety of functionality that makes distributed computing a lot easier to deal with. For example, it provides monitoring in which you could view the status of Ray jobs, actors, and tasks. It provides metrics, which allows you to see the overview of cluster resource utilization and Ray scheduling state. And allows you to do profiling, in which you could profile individual Ray workers across your cluster. But wait, there's more. Recently on Anyscale, we just released a RayTrain dashboard. This takes debugging distributed systems to the next level and focuses on ways that you could do debugging for distributed training in particular. Here's a few examples. With the RayTrain dashboard, you can monitor specifically things that you care about when you're doing distributed training, such as the status of training runs and training workers. You can also see metrics that go a little bit deeper, that have insights on the training throughput and training system operation time. And you could also do profiling that's much more specific to distributed training workloads that allow you to investigate bottlenecks, hangs, or errors from individual training worker processes. Sorry. Let's go through a quick example of how you might debug with the ray-trained dashboard. In this example, I want to debug a hanging worker. If you've done training, you might have seen this before. Your training has been running for a couple of hours, and suddenly it just stops. You have no idea why. With the ray-trained dashboard, we make it very easy to profile each individual worker. But first, let's say what you might do without the ray-trained dashboard. Without the ray-trained dashboard, you might need to, terminate your script, add a few print statements, rerun your script, SSH into individual machines, check the logs, or profile all the Python processes that you have running at that point in time. You have to massage all the data, figure out what's going on through this distributed environment. However, with the ray-trained dashboard, things are a lot easier now, in which you could easily navigate through the dashboard to find each train worker and look at its particular stack trace or logs. Taking the same example that we had from the previous slide, you can see here that I have an ongoing run, and I could look at the metadata to find exactly where, for example, my global rank 0 worker is, and I could click into a particular actor to see the logs for that particular actor, or I could do some profiling right there from the UI. It's as easy as that. The next challenge that I'm going to talk about after debugging is what happens if I actually run into an issue? What happens if I run into a hardware failure? This is really important in distributed training because hardware failures become a lot more prominent when you're scaling to a large cluster. Examples of hardware failures might include a GPU going down, or you might actually have a network interruption such that your nodes are no longer able to communicate with each other. Or if you're training with spot instances, your instance might get preempted. And at this point, you might be asking, how would I handle that situation? I'll show a very quick example of how ray-train implements fault tolerance to make it extremely easy to recover from these type of issues and more. In this example, assume that I'm training with ray-train on a cluster of 4 GPU nodes. The training is running very steadily, but at some point in time, a node fails. What will happen here is that ray-train will enter a recovering state, and it will pause and remove the node from the workers until it is able to get a new node. It'll stay requesting the GPU node until the cluster is able to scale back up, and once it does have its 4 nodes again, it'll be able to resume training there. Next, I'll show you how it is able to be implemented in ray-train as the user. Ray-train provides quite a few APIs to make this fault tolerance flow very, very simple to do. First, it provides a checkpoint interface and a report utility that allows you to save checkpoints from your distributed training workers and upload them to a cloud storage location. The second utility it provides is a get checkpoint utility that allows you to load your most recently saved checkpoint onto your distributed workers. And third, there's a max failures configuration that you could set in order to define how many retries you want your training application to support. And with that, with these few APIs, you're able to run distributed training with fault tolerance. In addition to this, ray-train also makes it easy to restore your training application across clusters, across jobs. To do this, it has a restore API, so if your entire ray cluster happens to terminate during a training job, you could simply relaunch the program on a separate cluster and call trainer.restore to the path where the experiment was saved. I'm also happy to announce that recently on Anyscale, we've taken this to the next level and released an extension of fault tolerance, which is elastic training. Elastic training means that you could scale your training job to a dynamic number of workers as opposed to a static number of workers. And when you do this, this means that you might have a max number of workers where your job will typically run, but your job now supports being able to train on fewer resources as well. This works particularly well with spot instances, where the capacity of spot instances might change over time, and you want to continue training even when you don't have a static set of spot instances available to use. Let's take a look at the example that we previously looked at in the fault tolerance page and see what happens when you have elastic training enabled. My job starts training with 4 GPUs again. Again, a node fails or a spot instance is preempted. Whereas previously, I would need to request another node and wait whoever knows how long in order for that node to be added back into the training job and then resume training from there. With elastic training, the ray train job can continue training on just 3 GPU nodes. It'll continue to request a new node and continue training on 3 GPU nodes until it's able to add that 4th node back into the training job. And from that point, it'll then be able to continue training again on that full capacity of 4 nodes. The best part of this is that the way to enable elastic training is, again, simply by changing one line of code in the scaling configuration. The last challenge that I'm going to talk about today in distributed training is, how do I deal with large data complexity? We all know that when you scale up your training workload, scaling the model is one problem, but scaling the data is a whole behemoth of its own. To go over how RayTrain solves this problem, I want to introduce the integration between the RayTrain library and the Ray data library, another Ray library in the Ray ecosystem that's built for large-scale data processing. If you look at the code snippet on the right, you could see kind of a quick example of how you could integrate Ray data with RayTrain to perform distributed data ingestion. First, you could take a look at the training function and think about what data processing and ingestion you want on the training worker itself. Here, RayTrain provides a simple get dataset shard API, which allows you to get the dataset shard that will be processed and read and trained on for that particular worker. The dataset shard itself has a simple API called iter-torch batches, which will allow you to convert this directly into a torch data loader-like object. Similarly, there are other integrations for other frameworks. Now that we've defined what the training logic looks like and how the training worker might consume the data, we also want to plug this together by defining exactly what data set will be fed into training. As you can see here, you could easily use RayData's APIs to read a data set from Parquet files and perform any pre-processing logic through a mat batches call. And lastly, to tie it all together, you could pass this into your torch trainer by passing it into the torch trainer as an argument that is a datasets dictionary. Just to summarize this integration, it's fantastic because it's Pythonic. It's very easy to define your dataset and pre-processing in the same script as your training code. It also supports automatic sharding, in which the dataset will be dynamically split across all of your training workers. So again, if you want to shard your dataset from 4 workers to 8 workers, all you need to do is modify your scaling config from RayTrain. And third, RayData is extremely scalable and supports streaming data loading and pre-processing to fit all your needs, which I'll dive into more detail in the next few slides. First, let's talk about pre-processing. With RayData, you can support last-mile pre-processing, in which you could perform dynamic, on-the-fly, online pre-processing logic without having to compute the entire data set. It also supports heterogeneous compute, in which you could scale pre-processing across your Ray cluster separate from your training scale. In the example below, you could quickly see that the RayData operations can be executed on purely CPU nodes, while the training function of your ray train application will be running on GPU nodes, all in the same ray cluster. Secondly, ray data also supports streaming ingestion. This means that you could do pipeline execution in which while your training workers are reading and training on one batch of data, ray data is reading in, pre-processing, ingesting the second batch of data, the following batch of data, and feeding it to your ray train workers. It's also very memory efficient, in which data will be read in one chunk at a time across your cluster, and it'll be discarded after training. So you don't ever have to load the entire data set into cluster memory or even cluster disk. On top of all this, ray data has a ton of optimizations on Anyscale that make it that much better to run with ray train. Two that I want to call out in particular for training. One is the streaming metadata fetching, in which metadata fetching previously was run in a blocking fashion as seen in the diagram in the top. And any of the reading or mapping or ingestion functionalities would have to wait until the metadata of the entire data set was fetched before proceeding. However, on Anyscale, this is now converted into a streaming operation. So as soon as metadata is fetched for the first chunk of data, you could start mapping over it, you could start ingesting it, and you could start training on it, saving a ton of time to get those immediate results that you need. Another optimization is a configuration optimizer of its own. On Anyscale, ray data can detect low resource utilization in the cluster or things such as memory pressure and optimize the configurations throughout your ray data pipeline and increase the performance of the data processing pipeline, improving the throughput of your training job. Cool. We've gone over some of the challenges and how ray train aims to solve these challenges. To tie this all together, I want to go over a quick case study of how we did pre-training of Stable Diffusion v2 earlier this year using ray train and ray data together. As a primer, here's a quick diagram that shows the architecture of Stable Diffusion. While doing training, you'll take in an image and caption pair, you'll pass them through some encoders, and you'll grab these latent embeddings and you'll feed them into a UNet diffusion model, which is the model that you're actually trying to train. A typical training pattern for this might look like this, where, very simply put, you're doing everything on each individual GPU. In this case, I have A100s, which will hold both the encoders as well as the UNet, and I'll do both the encoding stage as well as the training part of it all on one single GPU. We did some initial profiling when we ran it this way and noticed something very interesting. We saw through the GPU memory usage that the encoders were taking quite a bit of time, up to 30% of the entire training time. And we could also tell that it was not requiring so much memory to do these encodings, so we were looking for ways to see if we could optimize this and reserve these A100s simply for training the UNet itself. We took the original training pipeline and converted it so that we took the encoders out into a separate ray data offline job in which we would run the encoders as part of the ray data pre-processing stage and feed them directly to write into cloud storage in S3. Then, in our training job, we would use ray data again to read from S3 directly into the training workers. And in this scenario, only the UNet models are on the actual A100s, which means that they could fully utilize the GPU to themselves. The results were fantastic. With the original baseline, we saw a throughput of either 2,800 or 800 images per second based on the size of the images. However, by adding this extra offline pre-processing job, we were able to see increases of approximately 30% by simply converting to offline pre-processing. But we asked ourselves, what if we need dynamic pre-processing? What if we need to make sure that on every epoch, we randomly crop the images a little bit differently, and we need some more dynamic handling of this data? Can I still use offline preprocessing? We looked at the architecture again and thought, why not use Ray data for online preprocessing? We converted this two-cluster job back into a single cluster job in which we defined the Ray data pipeline and feed it directly into the Ray trainer, as we showed earlier in the Ray data quick start example. In this case, you could see that we're running the encoders on A10G instances, and we're running the diffusion model on A100s. And we could scale each of these workers separately based on the compute needs. The results were awesome. We saw similar results in that by adding a bunch of A10Gs, we were able to get the same throughput from the data pipeline that we did with offline preprocessing, with an equivalent gain over the original Torch data loader workload. And despite having to add more smaller instances to support this, the total cost for running this job over a single epoch was still able to be reduced by 10%. In addition to this, after taking a look at how to optimize the data pipeline, we also wanted to think, how do we optimize the training pipeline? Fortunately, as I mentioned before, RayTrain works well with the ML ecosystem, so we could leverage optimizations in the existing ecosystem, such as AWS EFA, PyTorch FSDP, and Torch Compile, in order to further optimize our training job to increase the throughput of the model by over 300%. To summarize this case study, we used RayTrain and RayData to pre-train Stable Diffusion v2. By using RayData as part of the preprocessing pipeline, we were able to increase the throughput by over 30% as compared to the Torch data loader. And by enabling training optimizations from the ML ecosystem, we were able to further increase the training throughput by actually over 300%. To summarize this talk, we went over a few of the challenges with distributed training and how RayTrain aims to address these. The first challenge was about setting up distributed environments and showed how RayTrain has a very simple, easy to understand API that abstracts away the distributed complexity. We talked about how you might wonder about how do I connect RayTrain to my existing ML workflow. And we covered how RayTrain has seamless integrations with the very fragmented ML ecosystem to make sure that you're not left out of the equation. We talked about the challenge of distributed debugging and showcased how RayTrain has the Ray dashboard and RayTrain dashboard for better distributed observability. We talked about how there are going to be more hardware failures when dealing with distributed systems, and how RayTrain has a nice fault tolerance mechanism as well as elastic training to support these failures. And lastly, we talked about dealing with large-scale data complexity and how integrating with Ray data can help solve these data ingestion and pre-processing problems. With that, thank you. I'll be around for questions if you have any.
On the topic of training with complex data, is it required that all shards of the data set be trained concurrently on workers concurrently, or can you custom configure the sharding so that there's more shards than workers and let the workers pick up the next shard as each one becomes available to do so?
You can do that, but that's a more advanced configuration that doesn't come out of the box.
Would that be done through the data config argument?
Yeah.
Okay. Can I talk to you offline about how to do that?
Yeah.
Thanks.
So one of the configurations I saw was you are able to segregate activities for the CPUs and the GPUs.
Yeah.
There are some machine types, let's say, for example, A3 in GCP, which comes with, let's say, 8 H100s in a single machine, could you specify like a job to only have a slice of that, the GPU, or?
You could shard it so you logically get scheduled on one of those GPUs. I'm not sure if that answers your question.
I mean, restrict, let's say if you have a job that requires more than one GPU, but then you want to restrict it to just 1 out of 8. Is that possible?
So this would probably be more of a general Ray core question, I assume. But to answer your question, you would probably have to shard it at a higher level. In which case, like Ray by itself won't shard your machine like at the physical level.
Okay, thank you.
So this is kind of a general question. So I see there's a ray train and there's also a ray tune. How do they kind of collaborate together? Or are they? Yeah.
Yeah, great question. So ray tune is meant for hyperparameter tuning. So the high level as a user, what you might want to think about is if you want to scale out one particular training job, you'll use ray train to support things such as data parallelism. But if you want to scale out to multiple trials of your job, you'll want to use ray tune to support multiple hyperparameter configurations. And you could also utilize these together if you want to leverage both at the same time.
Okay, because we are looking at the ML flow integration with ray train, but I couldn't find it on the official website, but I see it's integrated with ray tune. So I'm not sure how that works, like, because we're gonna try different, like not hyperparameter, but also the different runs about it. Yeah, I'm not sure if that's something like can be done with ray train as well.
Yeah, the APIs do work with ray train as well.
Okay.
But depending on what your needs are, you might want to use different APIs if you want things that are more granular, such as logging from individual training workers.
I see. Thank you.
Yeah.
Can you talk a little more about under the hood with ray train when it's performing its distributed training, how ray train using the backward pass of a deep learning model, how the various workers would receive their updates from each other?
Yeah, so in this case, it'll just use PyTorch distributed, and it'll probably use like Nickel under the hood to do gradient synchronization.
Is there does the user have to add any command to do that, or is that something that just through the ray.train.report, it just happens?
So it actually doesn't go through that path at all, actually.
Oh, okay.
So you'll be either using PyTorch DDP, for example, directly through that interface, or you could use RayTrain's prepare model interface, which we'll call DDP under the hood.
So either RayTrain prepare model or just PyTorch DDP?
That's right. Cool. Thank you.